Hello everyone, welcome to my channel. Today we're going to learn about the simple factory pattern, a common creational design pattern in software development. Let's start with a real-world example. Imagine you're renovating your home and need some furniture. You have two choices. The first is to put on a carpenter's apron, gather wood, glue, nails, and all the necessary tools, and make the furniture yourself at home. The second option is to contact a furniture factory and have them deliver ready-made furniture to your home. This way, you don't need to learn how to make furniture or deal with the problems that arise during the process. The simple factory pattern is similar to the second option. Now let's look at its definition. In simple terms, a simple factory generates an instance for the client without exposing any instantiation logic to the client. According to Wikipedia, in object-oriented programming, OOP, a factory is an object for creating other objects. Simply put, a factory is a function or method that returns objects of varying prototypes or classes from a method call, which typically creates new objects. Now, let's look at an example of a simple factory implemented in Java. First, I defined an interface called door. It has two methods that return the width and height of a door. Next, I defined a class wooden door that implements the door interface. It has two internal variables, width and height, which store the width and height of the door. It has a constructor that takes width and height as input and initializes these two instance variables. Then, there are two methods that read width and height. As you can see, wooden door is a concrete implementation of door. Finally, we define a simple factory class, doorFactory. It has a static method, makeDoor, that takes width and height as parameters. This method returns an instance of any class that implements the door interface. Inside the method, it creates a new wooden door instance and returns it. Let's look at an example of using this doorFactory. By calling the makeDoor static method on doorFactory and passing in the width and height, say 100 and 200, we can get an instance of door. We can then print out the width and height of this door. Similarly, we can use doorFactory to quickly create another instance of door, say door2, with a width of 50 and a height of 100. So, in what scenarios should we consider using the simple factory pattern? If object creation is complex, involving multiple steps or intricate logic, we can encapsulate this creation logic in a separate factory to avoid repetition and simplify our code. Hello everyone, welcome back to my channel. In this lesson, we will introduce the factory method design pattern. This is an important creational design pattern, ideal for scenarios where flexible object creation is needed. Imagine you are a hiring manager at a large company responsible for hiring suitable candidates for different positions. You can't possibly interview all the candidates yourself, so you need to delegate interviews to different colleagues based on the position. For example, technical positions are interviewed by the technical lead, and marketing positions are interviewed by the marketing lead. This way, you can focus on management and coordination rather than the interviews themselves. Now, let's look at the definition of the factory method. Simply put, the factory method design pattern is a creational design pattern that defines an interface for creating objects, but lets subclasses decide which class to instantiate. In other words, the factory method defers the instantiation process to the subclasses. Wikipedia explains the factory method as follows. In class-based programming, the factory method pattern is a creational design pattern. It uses factory methods to handle the problem of creating objects without specifying the exact class of the object that will be created. This is achieved by defining factory methods in an interface, implemented by subclasses, or by implementing the factory method in a base class and optionally overriding it in derived classes. The factory method design pattern usually includes the following components. 1. Product defines the interface for products. 2. Concrete product implements the product interface. 3. Creator declares the factory method that returns a product object. 4. Concrete creator implements the creator interface and the factory method, returning instances of concrete products. So why should we use the factory method design pattern? Here are a few benefits. 1. Decoupling the creation process. Separates the creation and usage of objects, reducing code coupling. 2. Enhanced flexibility. Inheritance and polymorphism make it easy to extend new classes without modifying existing code. 3. Improved code maintainability. Centralizes object creation logic in the factory method, making the code easier to maintain and extend. To better understand this pattern, let's implement a factory method in Java using the hiring manager example. First, we define an interviewer interface and create two classes that implement this interface, a developer and a community executive. Here, interviewer is equivalent to the product in the factory method, and developer and community executive are the concrete products. Next, we create an abstract hiring manager class that includes an abstract factory method, makeInterviewer, and an interview method, takeInterview. The takeInterview method calls the makeInterviewer factory method to create a specific interviewer and then conducts the interview. This hiring manager is equivalent to the creator in the factory method. Then, we create two concrete hiring manager classes: development manager for hiring developers and marketing manager for hiring marketing personnel. Here, development manager and marketing manager are equivalent to the concrete creators. Finally, the client can use these concrete hiring manager classes to conduct interviews. We instantiate a dev manager and a marketing manager, letting them handle their respective hiring tasks. So, in what scenarios should we use the factory method design pattern? When a class has some general processing logic, but the specific subclass can only be determined at runtime, the factory method pattern can be used. In other words, this pattern is useful when the client does not know which specific subclass needs to be instantiated. In conclusion, the factory method design pattern defines an interface for creating objects, allowing subclasses to decide which class to instantiate. This encapsulates the details of object creation, making the code more flexible and maintainable. In practice, we can use the factory method pattern to dynamically create different types of objects, enhancing code extensibility and readability. Hello everyone, welcome back to ByteVigor. In software development, we often need to create a set of related or dependent objects. For example, in a graphical user interface library, controls like buttons, text boxes, and menus need to work under the same style. Creating these objects directly in the code increases coupling, making the code harder to maintain and extend. The abstract factory design pattern provides a solution by defining an interface for creating related objects, allowing the client to create a set of related or dependent objects without worrying about their specific classes. Let's expand on the door example from this simple factory. Depending on your needs, you can buy a wooden door from a wood door store, an iron door from an iron door store, or a PVC door from a PVC door store. Additionally, you need different specialists to install these doors: a carpenter for wooden doors, a welder for iron doors, and so on. There is a dependency between the doors and the installers. Wooden doors need carpenters, iron doors need welders, etc. Now let's look at the definition of an abstract factory. Simply put, an abstract factory is a factory of factories. It provides a way to create related or dependent objects without specifying their concrete classes. By defining an interface for creating a series of related objects and having concrete factories implement this interface, clients can use these factories to create the required objects without worrying about the specific implementation details. Here is the UML class diagram representation of the abstract factory from Wikipedia. Its main components include 1. Abstract factory. Defines an interface for creating a set of product objects. This interface contains a series of methods, each corresponding to the creation of a product object. These methods are usually defined as factory methods to be implemented in the concrete factory classes. 2. Concrete factory. Implements the operations to create concrete product objects. Concrete factory classes implement the abstract factory interface and provide specific implementations to create different types of product objects. Each concrete factory is responsible for creating a set of related product objects. 3. Abstract product. Declares an interface for a type of product object. This interface defines common operations for product objects, which concrete product classes will implement. This allows client code to operate on product objects through this interface without needing to know the specific implementation details. 4. Product. Defines a concrete product object to be created. Concrete product classes implement the abstract product interface and provide specific operation implementations. These classes represent the actual objects being created, and clients obtain instances of these objects through factory classes. 5. Client. The client class uses the abstract factory interface to create and use product objects. It only uses the interfaces declared by the abstract factory and abstract product classes, without needing to know the concrete factory and product classes, achieving decoupling from specific implementations. To better understand this pattern, let's continue with the door example and demonstrate the abstract factory pattern using Java. We will create two factories that produce different types of doors and provide the corresponding installers. First, we define the door interface and its two concrete implementations, wooden door and iron door. In the UML class diagram, door is the abstract product, and wooden door and iron door are the concrete products. Next, we define a door fitting expert interface, representing the professionals who install the doors. We then implement two concrete specialists: carpenter, who installs wooden doors, and welder, who installs iron doors. In the UML class diagram, door fitting expert is also an abstract product, and carpenter and welder are the concrete products. Then we define an abstract factory interface door factory and two concrete factory classes: wooden door factory, which creates wooden door and carpenter, and iron door factory, which creates iron door and welders. Finally, the client uses these factories to create the corresponding doors and installers. We see that wooden door factory encapsulates the creation logic for wooden door and carpenter. Iron door factory encapsulates the creation logic for iron door and welder. This way, for each type of door, we won't mix up the installers. Moreover, the client operates entirely through interfaces, decoupled from the specific implementation details. When should we use the abstract factory design pattern? When you need to create a set of related or dependent objects and want to implement this through a unified interface, you can use the abstract factory pattern. This ensures that a series of created objects have a consistent style or theme, and the client code is decoupled from specific implementation details, facilitating later maintenance and extension. Let's summarize today's lesson. The abstract factory design pattern defines an interface for creating a series of related objects, allowing the client to separate itself from the creation process. This not only improves the flexibility and maintainability of the code, but also makes it easy to replace or add new object creation logic. In practical development, we can use the abstract factory pattern to manage complex object creation processes and improve code quality. Hello everyone, welcome back to my channel. In software development, sometimes we need to create a complex object, and the creation process involves multiple steps. The builder design pattern provides a solution, making the object creation process more flexible and controllable. Imagine you go to a burger joint and order a big burger, and they hand you the meal directly. This is an example of the simple factory pattern, but sometimes the creation process may involve more steps. For example, when you go to Subway and order a custom sandwich, you can choose different bread, sauces, cheese, etc. In this case, the builder pattern comes in handy. Let's take a look at the definition of the builder pattern. Simply put, the builder pattern allows you to create different variants of an object while avoiding the confusion of constructor parameters. It is very useful when you need to create objects in multiple steps. According to Wikipedia, the builder pattern is a creational design pattern aimed at solving the telescoping constructor anti-pattern. So, what is the telescoping constructor anti-pattern? In some cases, we see constructors like this. You can see that the number of parameters can quickly get out of control, and the order of the parameters can become confusing. Over time, if we want to add more options, the parameter list may continue to grow. This is what we call the telescoping constructor anti-pattern. To better understand the builder design pattern, let's use making a sandwich as an example and implement the pattern in Java. First, we define a sandwich class. It has 5 attributes. In its constructor, we pass in a sandwich builder class, which initializes all the attributes in the sandwich. Next, we define a sandwich builder class to configure the various attributes of the sandwich. Each attribute setting method, such as setSize, addCheese, addPepperoni, returns this for method chaining. Sandwich Builder also has a build method, which creates and returns a new sandwich instance based on the current configuration. Finally, we use the builder class to create a custom sandwich. First, create a sandwich builder instance with new, then initialize various attributes through method chaining, and finally call the build method to construct a sandwich instance. So, when should we use the builder design pattern? When an object has multiple variants and we want to avoid the confusion of constructor parameters, we can use the builder pattern. Unlike the factory pattern, which is suitable for one-step creation processes, the builder pattern is suitable for multi-step creation processes. In conclusion, the builder design pattern makes the object creation process more flexible and controllable by creating objects in steps while avoiding the confusion of constructor parameters. In actual development, the builder pattern can help us manage the creation process of complex objects, improving code maintainability and readability. Hello everyone, welcome back to Byte Vigor. In software development, sometimes we need to create an object and quickly make multiple copies of it. The prototype design pattern provides a solution by allowing us to create new objects by copying existing ones, thus simplifying the object creation process. Imagine you are an artist who has just finished a painting. Now, many people want a copy of this painting, but it is obviously not practical to repaint it each time. In this case, we can use a copier to quickly generate multiple copies of the painting. This is a real-life analogy for the prototype pattern. In simple terms, the prototype pattern allows you to create new objects by copying existing ones, without having to recreate every detail of the object. It is very useful when you need a large number of similar objects. According to Wikipedia, the prototype pattern is a creational design pattern that aims to create new objects by copying existing instances, thus avoiding the complexity or time-consuming operations of creating objects from scratch. So why should we use the prototype design pattern? There are several benefits. 1. Performance improvement. In some cases, copying an existing object is much faster than creating a new one. Especially when the initialization process is very complex, the prototype pattern can significantly improve performance. 2. Simplified object creation. Some objects may have many complex states and configurations, making manual creation cumbersome. With the prototype pattern, you only need to copy an existing object to easily create new ones. 3. Dynamic typing. The prototype pattern does not rely on specific classes, allowing you to dynamically create and configure new objects at runtime without modifying existing code. To better understand this pattern, let's use a simple shape class example to implement the prototype design pattern in Java. First, we define an abstract shape class with a clone method for cloning objects. This method implements the clonable interface and calls super.clone in the clone method, creating a copy of the current object. Here we assume that creating specific shapes is a complex and time-consuming operation. But by cloning, we can quickly replicate an object and improve creation performance. Next, we define concrete shape classes, such as circle and square, which extend the shape class and implement their own draw methods. Then, we create a shape cache class to cache different types of shape objects, and provide a getShape method to get a copy of an object by its ID. The shape cache class uses a hash table to cache shape objects. In the loadCache method, we create circle and square objects and cache them. Through the getShape method, we can find the corresponding prototype object in the cache by its ID and clone it to get a copy of the shape. Finally, we use the shapeCache class in the main method to get copies of shape objects. Here, we first call the shapeCache.loadCache method to preload the shape cache, which might be time-consuming but is a one-time operation. Then we use the shapeCache.getShape method to get clones of shape objects and print their types. The getShape method leverages caching and cloning, making it very fast regardless of how many times it is called. So, when should we use the prototype design pattern? When the cost of creating an object is high or the process is complex, and we need to quickly generate multiple copies of the object, we can use the prototype pattern. The prototype pattern creates new objects by copying existing instances, thus avoiding the overhead of repeatedly initializing objects. To summarize, the prototype design pattern makes the object creation process more efficient and flexible by copying existing objects. In actual development, the prototype pattern can help us quickly generate multiple copies of objects, improving the performance and maintainability of our code. Hello everyone, welcome to my channel. In today's lesson, we will introduce a very common and practical design pattern, the Singleton design pattern. The Singleton pattern ensures that a class has only one instance during runtime and provides a global access point. Let's dive in and learn more about it. Imagine that a country can only have one president at a time. Whenever a decision needs to be made by the president, only this single president can be found. The president in this example represents a singleton. This example vividly illustrates the concept of the Singleton pattern. According to Wikipedia, the Singleton design pattern is a creational design pattern that ensures a class has only one instance throughout the application and provides a global access point. In other words, the Singleton pattern guarantees that during the application's lifecycle, only one object of a class is created. So why do we use the Singleton pattern? There are several benefits to using this design pattern. 1. Resource saving. By limiting a class to only one instance, we can avoid significant resource consumption, especially for objects that are expensive to create. 2. Global access. The Singleton pattern provides a global access point, making it convenient to share and access the single instance across different parts of the application. 3. Control instance number. Ensuring only one instance throughout the application prevents multiple parts from creating and inconsistently using the same resource. Despite its usefulness, the Singleton pattern is also considered an anti-pattern and should be used with caution. The reasons include 1. Introducing global state. Changing the Singleton state affects other parts of the application, making debugging difficult. 2. Tight coupling. Using singletons increases coupling between code, making unit testing and mocking objects challenging. To better understand the Singleton design pattern, let's look at an example implemented in Java. First, we define a singleton class whose constructor is private and provides a static method to get its only instance. Next, we can get the unique instance of the singleton class through the getInstance method. In this example, we first obtain the unique instance of the singleton class by calling the getInstance method. Then call its showMessage method to display a message. As you can see, no matter how many times the getInstance method is called, the same instance is returned. In a multi-threaded environment, we need to ensure the singleton is thread safe. For this, we can use the double-checked locking mechanism, which ensures safe creation and access to the Singleton instance, even in a multi-threaded environment. Finally, let's summarize today's lesson. The Singleton design pattern is a simple yet crucial design pattern that ensures a class has only one instance and provides a global access point. Although it is sometimes considered an anti-pattern, it can still be highly effective when used in the right scenarios. Hello everyone, welcome back to Byte Vigor. In software development, sometimes we need to make two incompatible interfaces work together. The adapter design pattern provides a solution to this problem, allowing classes that otherwise couldn't work together due to incompatible interfaces to collaborate. Imagine you have some photos stored on a memory card that you need to transfer to your computer. For this, you need an adapter to connect the memory card to your computer's interface. In this case, a card reader acts as an adapter. Another common example is a power adapter. A three-pronged plug cannot directly fit into a two-hole socket, so you need a power adapter to convert it to a compatible interface. Another example is a translator who translates one person's speech to another. In simple terms, the adapter pattern allows you to wrap an incompatible object in an adapter so that it becomes compatible with another class. According to Wikipedia, in software engineering, the adapter pattern is a structural design pattern that allows the interface of an existing class to be used as another interface. It is often used to make existing classes work with others without modifying their source code. To better understand this pattern, let's take a simple video player program as an example and implement an adapter using Java. This program currently can only play MP4 format videos, but we want it to also play VLC and AVI formats. For this, we need to introduce an adapter. First, we define a media player interface that has only one method called play. Next, we define an advanced media player interface that has two play methods for playing VLC and AVI format files, respectively. Then, we implement the advanced media player interface in two concrete classes, VLC player and AVI player. After that, we create an adapter class called Media Adapter, which implements the media player interface and forwards the requests to an advanced media player object. By introducing this media adapter as an intermediate forwarding layer, we enable our player, which originally did not support advanced formats, to play advanced format media files indirectly. Finally, we create a video player class called Video Player that implements the media player interface. This class can play MP4 format files, and through the adapter, can also play VLC and AVI format files. So when should we use the adapter design pattern? When you want to reuse some existing classes but their interfaces are incompatible with the current system, you can use the adapter pattern. The adapter pattern helps you convert the interface of a class into another interface, allowing classes with incompatible interfaces to work together. To summarize, the adapter design pattern creates an intermediate layer that allows two incompatible interfaces to work together. In actual development, the adapter pattern helps us reuse existing code and improves the flexibility and maintainability of the system. Hello everyone, welcome back to Byte Vigor channel. In software development, sometimes we need to add a layer between abstraction and implementation to better decouple them. The bridge design pattern offers a solution that allows the abstraction and implementation parts to change independently. Imagine you have a website with different pages, and you want to allow users to change the theme. What would you do? Create multiple versions of each page for each theme? Or create separate themes and load them based on user preferences? The bridge pattern allows you to do the latter, that is, create separate themes and load them based on user choices. Simply put, the bridge pattern is about favoring composition over inheritance. It moves implementation details from one hierarchy to another object with a separate hierarchy. According to Wikipedia, the bridge pattern is a structural design pattern that decouples an abstraction from its implementation so that the two can vary independently. To better understand this pattern, let's take a simple example of a shape class implemented in Java. Suppose we have different shapes, like circles and squares, and different colors, like red and green. We want to be able to combine shapes and colors freely without creating new classes for each combination. First, we define a color interface, color, with a fill method. Then, we define concrete color classes, such as red and green, which implement the color interface. Next, we define an abstract shape class, shape, that holds a reference to a color interface and defines an abstract draw method. Then, we define concrete shape classes, such as circle and square, which extend the abstract shape class and implement the draw method. Now we can freely combine shapes and colors and call the draw method. Here, we create a red circle and a green square and call their draw methods. As you can see, with the bridge pattern, shapes and colors can be combined flexibly without creating separate classes for each combination. When should we use the bridge design pattern? When you want to decouple the abstraction part and the implementation part so that they can vary independently, you can use the bridge pattern. The bridge pattern helps you expand your system more flexibly without modifying existing code. Finally, let's summarize the content of this lesson. The bridge design pattern separates the abstraction part from the implementation part so that they can change independently. In actual development, the bridge pattern can help us create more flexible and extensible systems, improving code maintainability. Hello everyone, welcome back to ByteVigor channel. In software development, sometimes we need to handle hierarchical structures of objects, such as files and folders in a file system. The composite design pattern provides a solution that allows us to treat individual objects and compositions of objects uniformly. Imagine you have a file system that contains files and folders. Folders can contain files or other folders. You want to handle files and folders uniformly, such as calculating their size or displaying their contents. The composite pattern allows you to create a tree structure to represent files and folders and handle them in a consistent way. Simply put, the composite pattern allows you to compose objects into tree structures to represent part-whole hierarchies. The composite pattern makes the client treat individual objects and compositions of objects uniformly. According to Wikipedia, the composite pattern is a structural design pattern that describes a group of objects that are to be treated in the same way as a single instance of an object. Implementing the composite pattern allows clients to treat individual objects and compositions uniformly. To better understand this pattern, let's use a simple file system example and implement the composite design pattern in Java. Suppose we have different types of files, such as text files and image files, and their composite objects, such as folders. First, we define a file interface with two methods, show and add. Then, we define concrete file classes, such as text file and image file, which implement the file interface. Note that while text file and image file implement the file interface, they only support the show operation and do not support adding. Next, we define a folder class, which also implements the file interface and contains a list of file objects to store its children. Now, we can create files and folders and call their show methods. In code here, we created a text file and an image file and added them to a folder. Then, we called the folder show method to display all its children. As you can see, although the folder is a composite object, we can still treat it like a single file and handle it uniformly. So, when should we use the composite design pattern? When you want to compose objects into tree structures to represent part-whole hierarchies, you can use the composite pattern. The composite pattern helps you handle individual objects and compositions uniformly. Finally, let's summarize today's lesson. The composite design pattern allows you to compose objects into tree structures, making the client treat individual objects and compositions uniformly. In actual development, the composite pattern can help us create more flexible and extensible systems, improving code maintainability. Hello everyone, welcome back to ByteVigor channel. In software development, sometimes we need to add new functionality to objects dynamically without altering their structure. The Decorator design pattern provides a flexible solution that allows us to extend an object's functionality at runtime without modifying the original code. Imagine you are at a coffee shop ordering a coffee. You can customize your coffee with additions like cream, syrup, or chocolate. These additions do not change the basic structure of the coffee, but enhance its features and flavor. The decorator pattern is like adding these toppings to your coffee, dynamically adding new functionalities to an object. Simply put, the decorator pattern allows us to add new functionality to an object dynamically without modifying the original code. This is achieved by creating decorator classes that wrap the original object and add new behaviors or attributes. According to Wikipedia, in object-oriented programming, the decorator pattern is a structural design pattern that allows behavior to be added to individual objects, either statically or dynamically, without affecting the behavior of other objects from the same class. The decorator pattern is particularly useful for adhering to the single responsibility principle, as it allows functionality to be divided between classes with unique areas of concern. To better understand this pattern, let's take a simple example of a coffee class in Java. Suppose we have different types of coffee, like simple coffee, espresso, and various decorations, like milk, syrup, that can be added to them. First, we define a coffee interface, coffee, with two methods, one to get the cost and another to get the description. Next, we define concrete coffee classes such as simple coffee and espresso, which implement the coffee interface. Then, we define an abstract decorator class, coffee decorator, that implements the coffee interface and contains a reference to a coffee object. Next, we define concrete decorator classes, such as milk decorator and sugar decorator, which extend the coffee decorator abstract class and add new functionalities to the existing coffee. For example, after applying the milk decorator, the cost of the decorated coffee will increase by 2, and the description will include milk. Now we can create coffee objects and dynamically add decorations to them. In the code here, we first create a simple coffee, then add milk and sugar decorations, and output the description and cost after each decoration. As you can see, each time a decoration is added, the coffee's description and cost are dynamically updated without modifying the original coffee class. This demonstrates the power of the decorator pattern, which allows us to flexibly add various functionalities to objects without changing their underlying structure. When should we use the decorator design pattern? When you want to dynamically add new functionality to an object without modifying the original code, you can use the decorator pattern. The decorator pattern helps you flexibly and extensively combine various functionalities for objects. Finally, let's summarize the content of this lesson. The decorator design pattern allows us to dynamically add new functionality to an object without modifying the original code. By creating decorator classes, we can flexibly enhance an object's features at runtime. In actual development, the decorator pattern can help us create more flexible and extensible systems, improving code maintainability. Hello everyone, welcome back to ByteVigor channel. In software development, sometimes we need to simplify the interfaces of complex systems to make them easier to use and maintain. The Facade design pattern provides a solution by offering a unified interface for a complex system, making the system easier to use and understand. Imagine you are staying at a hotel. The hotel offers many services such as room service, restaurant reservations, and laundry service. If you need to use these services, you don't need to contact each department separately. You just call the front desk, and they will arrange everything for you. The front desk acts as a facade here, simplifying your interaction with the hotel's complex service system. Simply put, the facade pattern provides a unified interface to a set of interfaces in a subsystem. The facade defines a higher-level interface that makes the subsystem easier to use. According to Wikipedia, the facade pattern is a structural design pattern that provides a consistent interface to a set of interfaces in a subsystem. To better understand this pattern, let's take a simple example of a home theater system and implement the facade design pattern in Java. Suppose we have multiple subsystems like a DVD player, a projector, a sound system, and a screen. First, we define the classes for these subsystems, each with some basic operations. For example, the DVD player has operations like on, off, and play. The sound system has operations like on, off, and set volume. Next, we define a home theater facade class that encapsulates all these subsystems and provides a simplified interface to operate them. Watching a movie involves several steps, such as lowering the screen, turning on the projector, setting the projector input to DVD, turning on the sound system, setting the volume to 10, turning on the DVD player, and finally playing the movie. Ending the movie involves reversing these steps. By using the facade, users only need to call two simple methods, watch movie and end movie, significantly simplifying their operations. Now we can create the subsystems of the home theater system and operate them through the facade. In the code here, we use the home theater facade class to easily control multiple subsystems, simplifying user operations. When should we use the facade design pattern? When you need to simplify the interface of a complex system, you can use the facade pattern. The facade pattern helps you provide a unified interface to operate complex subsystems, making the system easier to use and maintain. Finally, let's summarize the content of this lesson. The facade design pattern provides a unified interface for a complex system, making it easier to use and understand. In actual development, the facade pattern can help us create more concise and maintainable systems, improving code readability. Hello everyone, welcome back to ByteVigor. In software development, when we need a large number of similar objects, creating and storing each object separately can consume a lot of memory. The Flyweight design pattern offers a solution by sharing similar objects to reduce memory usage and improve performance. Imagine you're creating a massive multiplayer online game, MMORPG. There are thousands of trees, buildings, and other scene elements in the game. If each element is created separately, it would take up a lot of memory. Instead, we can share the same image data for similar elements and only store their position information when necessary. This is the core idea of the Flyweight pattern, saving memory by sharing the same objects. Simply put, the Flyweight pattern reduces memory usage by sharing objects. It uses a factory to manage these shared objects and ensures that each object is created only once. According to Wikipedia, the Flyweight pattern is a structural design pattern that efficiently supports a large number of fine-grained objects by sharing them across multiple contexts. To better understand this pattern, let's use a simple drawing program as an example and implement the Flyweight design pattern in Java. Suppose we need to draw a large number of circles on the screen. First, we define a circle interface with two methods, draw and set position. Next, we define a concrete circle class that implements the circle interface. Then, we define a circle factory class to manage and create shared circle objects. The circle factory class uses a hash map as a cache. In the getCircle method, for a specific color, it first checks if it can share the corresponding circle from the cache. Only if it is not in the cache does it create a new one, store it in the cache, and return it. Now, we can use the circle factory class to create and manage circle objects and draw them on the screen. In this code, we create and manage circle objects using the circle factory. Each time we need a circle object, we first check if a circle object of the same color already exists. If not, we create a new circle object and store it in the circle map. If it exists, we directly return the existing object. This way, we can draw multiple shared circle objects on the screen without creating a separate object for each circle. When should we use the Flyweight design pattern? You can use the Flyweight pattern when you need to create a large number of similar objects and want to reduce memory consumption by sharing objects. The Flyweight pattern can help you optimize performance and improve the scalability of your system. Finally, let's summarize this lesson. The Flyweight design pattern reduces memory usage and improves performance by sharing objects. In actual development, the Flyweight pattern can help us create more efficient systems, especially in scenarios where a large number of similar objects are needed. Hello everyone, welcome back to ByteVigor channel. In software development, there are times when we need to provide a proxy for an object to control access to it. This is where the proxy design pattern comes in. The proxy pattern uses a proxy object to control access to the actual object, providing an indirect way to access it. Imagine you are a landlord, but you don't want to deal with tenants' various needs and issues directly, so you hire an agent to handle them for you. This agent acts as a proxy for the property, dealing with the tenants while you only need to communicate with the agent. This way, you don't have to face the tenants directly. This is the basic concept of the proxy pattern, controlling access to the actual object through a proxy. Simply put, the proxy pattern provides a proxy for other objects to control access to them. According to Wikipedia, a proxy in its most general form is a class that functions as an interface to something else. A proxy is a wrapper or agent object that the client calls to access the real serving object behind the scenes. Using a proxy can simply forward requests to the actual object or provide additional logic. Extra functionality can be provided in the proxy, such as catching when operations on the actual object are resource-intensive, or checking preconditions before calling operations on the actual object. To better understand this pattern, let's take a simple security door program as an example, using Java to implement the proxy design pattern. First, we define a door interface and a concrete door implementation. Here, the door interface defines two basic methods, open and close. The LabDoor class implements the door interface and defines the specific behavior for opening and closing the door. Next, we create a proxy class, securedDoor, to protect the door we want to secure. The securedDoor class also implements the door interface, but it adds an authentication step when calling the open method. The constructor accepts a door object and stores it in the door member variable. The open method first calls the authenticate method to verify if the password is correct. If the password is correct, it calls the open method of the actual door object. Otherwise, it prints an error message. The close method directly calls the close method of the actual door object. Here's an example of how to use the proxy. In this example, we create a secured door object and pass in a LabDoor object. We attempt to open the door with an incorrect password, and the system indicates it cannot be opened. When we use the correct password, the door opens smoothly and then closes. Through this example, we can clearly see how the proxy pattern controls access to the actual door, LabDoor. The proxy object, securedDoor, adds a security step, providing protection for the door without needing to change the original door's implementation. This pattern offers a flexible and secure way to manage access to objects. The proxy pattern can be used not only for the security door example, but also for implementing data mappers. For example, I recently used this pattern to write an object data mapper, ODM, for MongoDB. I wrote a proxy on top of the Mongo classes and utilized the magic method __call. All method calls were proxied to the original Mongo class, and results were returned as is. But in the case of find or find1, data was mapped to the desired class objects instead of returning a cursor. So, when should we use the proxy design pattern? You can use the proxy pattern when you need to perform additional operations when accessing an object. Examples include lazy loading, access control, and logging. The proxy pattern can help you control access to objects without modifying existing code. Finally, let's summarize today's lesson. The proxy design pattern controls access to the actual object through a proxy, providing an indirect way to access it. In actual development, the proxy pattern can help us create a more flexible system structure and improve code maintainability and scalability. Hello everyone, welcome back to the Byte Vigor channel. In software development, sometimes we need to distribute the responsibility of handling requests among multiple objects to avoid coupling between the sender and receiver of the request. This is where the chain of responsibility design pattern comes in. Using this pattern, a request is passed along a chain until an object handles it. Imagine a leave approval process in a company. When an employee submits a leave request, it first goes to their direct supervisor. If the supervisor approves it, the request is completed. If not, the request is automatically passed up to the next higher-level supervisor until someone handles it. This is the basic concept of the chain of responsibility. A request can be processed by multiple handlers until one of them processes it. Simply put, the chain of responsibility pattern helps us build a chain of objects. A request enters from one end of the chain and is passed along until it finds a suitable handler. According to Wikipedia, the chain of responsibility is a behavioral design pattern that decouples the sender and receiver of a request by connecting multiple handlers in a chain. The request is then passed along the chain until it is processed by one of the handlers. To better understand this pattern, let's demonstrate it with a simple account program. Suppose you have 3 payment accounts: a bank account, a PayPal account, and a Bitcoin account. The bank account has $100, the PayPal account has $200, and the Bitcoin account has $300. The payment priority is bank, PayPal, and Bitcoin. Now you want to buy an item worth $259. Using the chain of responsibility pattern, you first check if the bank account can pay. If it can, the payment is completed and the chain ends. If not, the request is forwarded to the PayPal account. If the PayPal account also can't pay, the request is forwarded to the Bitcoin account. The bank, PayPal, and Bitcoin accounts are like links in the chain, and this whole process is how the chain of responsibility works. Let's look at the code implementation. First, we define a basic account class. The account class is an abstract class that represents a payment account and implements the basic structure of the chain of responsibility pattern. It includes a successor variable to point to the next account in the chain and a balance variable to represent the account balance. Through the setNext method, accounts can be linked into a chain, forming a sequence to handle requests. In the pay method, the program first checks if the current account has enough balance to pay the requested amount. If it does, the payment is made and payment information is printed. If the balance is insufficient and there is a next account, the request is forwarded to the next account. If all accounts cannot pay, an exception is thrown. Specific account types like bank, PayPal, and Bitcoin inherit from account and initialize the balance through their constructors. Now we can use these defined links, that is bank, PayPal, and Bitcoin, to set up the chain of responsibility. In this example, we create a payment chain where the bank account is linked to the PayPal account, and the PayPal account is linked to the Bitcoin account. When we try to pay $259, the request starts with the bank account. Since the balance is insufficient, the request is forwarded to the PayPal account, still insufficient, and then forwarded to the Bitcoin account, which finally completes the payment. You can see that the chain of responsibility pattern allows us to handle requests with a series of handlers without knowing in advance which specific handler will process the request. This pattern makes the system more flexible and allows adding or removing handlers easily without affecting other parts of the code. So, when should we use the chain of responsibility pattern? You can use it when you have multiple objects that can handle a request, but the specific object that handles it is determined at runtime. The chain of responsibility pattern can simplify the connections between objects and avoid coupling between the request sender and receiver. Finally, let's summarize the content of this lesson. The chain of responsibility design pattern distributes the responsibility of handling a request among multiple objects, avoiding coupling between the sender and receiver. In actual development, the chain of responsibility pattern can help us create a more flexible system structure, improving the maintainability and scalability of the code. Hello everyone, welcome back to Byte Vigor channel. Today, we will explore the command design pattern, a widely used behavioral design pattern in software development. This pattern is used to encapsulate actions as objects, allowing for parameterization and decoupling of requests. Imagine you're at a restaurant ordering food. You, the client, tell the waiter, the invoker, what dish you want, the command. The waiter then passes this request to the chef, the receiver, who prepares the dish based on the request. Another example is you, the client, using a remote control, the invoker, to turn on the TV, the receiver. The buttons on the remote control are the commands. Simply put, the command pattern allows you to encapsulate actions as objects, decoupling the client from the receiver. According to Wikipedia, the command pattern is a behavioral design pattern in which an object is used to encapsulate all the information needed to perform an action or trigger an event at a later time. This information includes the method name, the object that owns the method, and the parameters for the method. To better understand this pattern, let's use a simple example of controlling a light bulb with a remote control implemented in Java. First, we define the receiver, which is the object that actually performs the action. In this case, the receiver is the bulb class, which has two methods, turn on and turn off. Next, we define a command interface, which includes methods for executing, undoing, and redoing commands. Then, we create two concrete command classes, turn on and turn off, both of which implement the command interface. The turn on class is used to turn on the bulb, and the turn off class is used to turn off the bulb. After that, we define an invoker class, here the remote control, which is responsible for invoking commands but does not know the details of their implementation. The remote control class has a submit method that receives and executes command objects. Finally, we have the client code. We first create the receiver object, bulb, then create the turn on and turn off commands, and then create an invoker object, remote control. We submit the turn on and turn off commands to the invoker object, remote control, in sequence. In this way, the client doesn't need to know the details of the operation's implementation, but can execute actions through command objects. So, when should we use the command pattern? The command pattern is perfect for implementing features like scheduling, logging, undo, and redo. When you need to encapsulate operations as objects and control behavior through the arrangement of these operations, the command pattern is very useful. In summary, the command design pattern encapsulates requests as objects, allowing the system to support complex command, request, and operation management. It offers a flexible way to extend system functionality while maintaining decoupling between the invoker and the receiver. Hello everyone, welcome back to the ByteVigor channel. Today, we are going to explore the Iterator design pattern, a widely used behavioral design pattern in software development. This pattern allows you to access and traverse elements in a collection without exposing its underlying implementation. Imagine you have an MP3 player. You can press the next or previous buttons to browse through consecutive songs. Similar devices include radios and televisions, which provide interfaces that allow you to traverse different stations or channels. The Iterator design pattern is like these device interfaces. It provides a way to sequentially access elements in a collection without exposing its internal implementation. According to Wikipedia, the Iterator pattern is a behavioral design pattern used to traverse elements in a container. The Iterator pattern decouples algorithms from containers. To better understand this pattern, let's implement it in Java using a simple example of a bookshelf. First, we define a collection interface that includes a method to create an iterator. Then, we define a concrete collection class, bookshelf, which implements the collection interface. In this class, we use a list to store books and provide an addBook method to add books. The createIterator method returns a bookshelf iterator instance to traverse the books. Next, we define an iterator interface that includes two methods for traversing elements, hasNext and next. Then we define a concrete iterator class called bookshelfIterator, which implements the iterator interface and maintains the current position of the traversal. In this class, the hasNext method checks if there are more elements, and the next method returns the current element and moves the index to the next position. Finally, let's look at the client code. In this example, we first create a bookshelf instance and add several books. Then, we create an iterator instance by calling the createIterator method on the bookshelf instance. Next, we use a while loop to check for more books using the hasNext method and get the current book title with the next method, printing it out. As you can see, the iterator pattern allows us to traverse elements in a collection in a uniform way without knowing its internal implementation. So, when should you use the iterator design pattern? When you need to traverse elements in a collection consistently without exposing its internal representation, you can use the iterator pattern. The iterator pattern provides a decoupled way to traverse collection elements while keeping the code simple and flexible. Hello everyone, welcome back to ByteVigor channel. Today, we will explore the Mediator design pattern, a widely used behavioral design pattern in software development. This pattern helps reduce the complexity of communication between objects and promotes decoupling. Imagine you are a class teacher who needs to communicate with each student to understand their learning progress and issues. Directly communicating with each student can be time-consuming and complicated. So, you assign a class monitor to collect information from each student and relay it to you. The class monitor acts as a mediator, simplifying communication between you and the students. In simple terms, the mediator pattern introduces a third-party object, called the mediator, to control the interaction between two or more objects, called colleagues. This reduces the coupling between classes as they no longer need to know each other's implementation details. According to Wikipedia, the mediator pattern defines an object that encapsulates how a set of objects interact. This pattern is considered a behavioral pattern because it can change the program's running behavior. The difference between the mediator pattern and the proxy pattern is that the mediator pattern focuses on simplifying communication between objects by managing and coordinating their interactions through a mediator. The proxy pattern, on the other hand, controls access to an object, often adding extra functionality like access control or lazy loading. In other words, the mediator pattern is used for coordinating communication, while the proxy pattern is used for controlling access. To better understand this pattern, let's implement a simple chat room program in Java using the mediator pattern. First, we define an abstract mediator interface, chat mediator, that includes methods for sending messages and adding users. Next, we define a concrete mediator class, chat mediator impl, that implements the chat mediator interface and manages a group of users. The send message method sends messages to all users, and the add user method adds users to the chat room. Then, we define an abstract user class that includes methods for sending messages and receiving messages. After that, we define a concrete user class, user_impl, that implements the abstract methods send and receive from the user class. Finally, let's look at the client code. In this example, we first create an instance of chat mediator impl, then create several users and add them to the chat room. Whenever a user sends a message, other users receive it. In the code, chat mediator impl manages the users and handles message transmission. Each user sends messages using the send method, and chat mediator impl forwards the message to other users, who receive it through the receive method. As you can see, the mediator pattern simplifies communication between objects by introducing a mediator. Objects no longer reference each other directly, but communicate through the mediator. This significantly reduces coupling between objects, making the system easier to maintain and extend. So, when should you use the mediator pattern? When you want to reduce complex dependencies between objects and promote decoupling, you can use the mediator pattern. It simplifies communication and interaction between objects, making the system structure clearer and more maintainable. Finally, let's summarize today's lesson. The mediator design pattern introduces a mediator object to reduce complex communication and dependencies between objects, making the system easier to maintain and extend. In actual development, the mediator pattern can help us build more flexible and loosely coupled systems, improving code maintainability. Hello everyone, welcome back to Byte Vigor channel. Today, we will explore the Memento design pattern, a widely used behavioral design pattern in software development. This pattern is used to save and restore the state of an object without breaking its encapsulation. Imagine you are writing a long document and want to save its current state at certain points so you can revert to a previous version if needed. This saving operation is similar to the memento in the Memento design pattern. Another example is the save feature in video games, where players can save their progress and load it later. According to Wikipedia, the Memento pattern is a behavioral design pattern that captures an object's internal state without violating encapsulation and allows the state to be restored later. To better understand this pattern, let's use a simple text editor as an example to implement the Memento pattern in Java. First, we define a Memento class that stores the state of an object. The Memento class contains a single string representing the state and provides a constructor to initialize it. It also offers a getState method to retrieve the saved state. Next, we define a text editor class, which is the object whose state we want to save and restore. It contains a string builder to represent the current content. The type method allows us to input text and add it to the content. The save method creates a Memento object to save the current content, and the restore method restores the content from a Memento object. Then, we define a caretaker class responsible for managing the saving and restoring of Memento objects. It includes a list to store multiple Memento objects. The add Memento method adds new Memento objects to the list, and the getMemento method retrieves a Memento object at a specified index. Finally, let's look at the client code. In this example, we first create a text editor object for text editing and a caretaker object to manage the state of the text editor. First, we type the text hello and save the current state to a Memento, managed by the caretaker. Then we type world and save the current state again. Next, we retrieve the first saved Memento from the caretaker and restore it to the text editor. After restoration, the printed content is hello, which is the content from our first save. Then, we retrieve the second saved Memento from the caretaker and restore it to the text editor. After restoration, the printed content is hello world, which is the content from our second save. This way, we demonstrate how to use the Memento pattern to save and restore the state of an object. The key to this pattern is that it allows us to manage the state without breaking the encapsulation of the object. So, when should we use the Memento design pattern? You can use the Memento pattern when you need to capture and restore the state of an object without violating encapsulation. For example, it's beneficial when implementing undo-redo functionality. The Memento pattern helps store the state of an object and restore it when needed. To summarize, the Memento design pattern provides a way to manage the state of an object without breaking its encapsulation by saving and restoring its state. In actual development, the Memento pattern can help us create more flexible and maintainable systems, improving code readability and maintainability. Hello everyone, welcome back to ByteVigor. Today we're going to explore the Observer Design Pattern, a widely used behavioral design pattern in software development. This pattern is used to define a one-to-many dependency between objects, so that when one object's state changes, all dependent objects are notified and automatically updated. Imagine you've subscribed to a YouTube channel. When the channel uploads a new video, you receive a notification. This is a perfect example of the observer pattern in action. The YouTube channel is the subject being observed, and you are the observer. When the channel has new content, all subscribers are notified. Simply put, the observer pattern defines a dependency where, when one object's state changes, all objects that depend on it are notified and updated automatically. According to Wikipedia, the observer pattern is a behavioral design pattern in which an object, known as the subject, maintains a list of its dependents, known as observers. When the subject's state changes, it automatically notifies all its observers. To better understand this pattern, let's use a simple job recruitment system as an example and implement the observer pattern in Java. First, we define a job post class to store job information. Next, we define an observer interface that includes a notification method called onJobPosted. Then, we create a concrete observer class, such as JobSeeker, that implements the observer interface and handles job posting notifications in the onJobPosted method. Next, we define an observable interface that includes methods for registering, unregistering, and notifying observers. After that, we create a concrete observable class, like Employment Agency, which implements the observable interface and maintains a list of observers. The attach method is used to register observers, while the detach method unregisters them. When a new job is posted, the addJob method calls notify observers, which iterates through all observers and calls their onJobPosted method to notify them of the new job. Finally, let's look at the client code. In this example, we create two job seekers who act as observers, John Doe and Jane Doe. Then, we create an employment agency object called agency, which acts as the observable or subject, and attach the two job seekers to it. When we add a new job, the agency notifies all attached observers. So, when should you use the observer design pattern? Use the observer pattern when you want to notify multiple objects of a state change in another object without tightly coupling them. For instance, it's ideal for event handling systems, message broadcasting systems, or any scenario where you need to dynamically notify multiple objects. To wrap up, the observer design pattern helps by defining a one-to-many dependency between objects, so that when one object's state changes, all its dependents are notified and automatically updated. This pattern is especially useful in systems that need to handle event notifications, such as job recruitment sites or event-driven systems. Hello everyone, welcome back to the Byte Vigor channel. Today we're going to explore the visitor design pattern, a widely used behavioral design pattern in software development. The core idea behind this pattern is to add new functionality to objects without modifying their existing structure. This is particularly useful in scenarios where the object structure is stable, but you frequently need to extend its behavior with new operations. Imagine you are an art critic invited to visit a large museum. Each gallery displays different types of artwork, such as paintings, sculptures, and ceramics. You simply follow a museum guide who explains the background and value of each piece, without the need for you to gather this information repeatedly for each exhibit. The visitor pattern is like this museum guide, allowing you to add new explanations or features to each exhibit without altering the exhibits themselves. According to Wikipedia in object-oriented programming, the visitor design pattern separates algorithms from the objects they operate on, allowing you to add new operations without modifying the object's structure. This aligns with the open-closed principle from the solid design principles. To better understand this pattern, let's take a look at a zoo simulation example, implemented in Java. In this example, we have several different animals, including monkeys, lions, and dolphins. First, we define an animal interface with an accept method, which will be used to accept visitors. Next, we define a visitor interface, animal visitor, which specifies visit methods for each type of animal. This interface allows us to easily add new operations for different animals. After that, we implement specific classes for each animal and include the accept method in each one. Each accept method directs the operation to the appropriate visitor method. Then, we create a concrete visitor class that performs specific operations. For example, the speak class implements the animal visitor interface and defines the unique sound behavior for each animal, such as the monkey's shout, the lion's roar, and the dolphin's speak. Now let's look at the client code. In this example, we create a monkey, a lion, and a dolphin, and have them accept the speak visitor, allowing them to make their respective sounds. Next, let's see how we can add new operations without modifying the existing object structure. For instance, if we want to add a jumping behavior to these animals, we simply create a new visitor class, jump, and define the specific jump behavior for each animal. Then, we can use it in the client code. As you can see, with the visitor pattern, we can add new operations like jump to the animals without altering their structure, showcasing the pattern's flexibility and extensibility. So, when should you consider using the visitor design pattern? This pattern is ideal when you need to add new functionality to objects without modifying their structure. It's particularly useful in scenarios where the object structure is stable, but new operations are frequently needed. By using the visitor pattern, you can separate operations from the object structure, ensuring stability while allowing for flexible additions. To summarize, the visitor design pattern introduces a visitor object that enables you to add new functionality to objects without modifying their structure. In real-world development, the visitor pattern helps maintain the open-closed principle, enhancing the system's extensibility and maintainability. Hello everyone, welcome back to the Byte Vigor channel. Today we're going to explore the strategy design pattern, a widely used behavioral design pattern in software development. The core idea of this pattern is to define a family of interchangeable algorithms and allow them to vary independently of the client that uses them. In other words, the strategy pattern lets us choose an algorithm at runtime without needing to modify the client code. Imagine you're shopping at a mall, and when it's time to check out, You can choose different payment methods like a credit card, debit card, or mobile payment. Each payment method has a different processing flow, but the ultimate goal is to complete the payment. Here, the payment method is a strategy. You can select different payment options depending on the situation without changing any other part of the shopping process. Simply put, the strategy pattern allows you to define a set of algorithms and encapsulate them in independent classes so that they can be used interchangeably. According to Wikipedia, the strategy design pattern is a behavioral design pattern that separates the definition of algorithms from their usage, allowing the algorithms to vary independently of the client code. To better understand this pattern, let's implement it in Java using a simple payment system example. In this example, we have several different payment methods, such as credit card payment, PayPal payment, and Bitcoin payment. First, we define a payment strategy interface, which includes a pay method to execute the payment operation. Next, we implement different payment method classes, each of which implements the payment strategy interface and defines the specific payment logic. Then, we create a shopping cart class that uses a payment strategy to complete the payment. In the shopping cart class, we define a pay method that accepts a payment strategy object and calls the strategy's pay method to process the payment. Finally, let's look at the client code. In this example, we create a shopping cart object and add some items to it. Then, depending on the scenario, we can use different payment strategies to complete the payment. For instance, in a physical store, we might use a credit card, while for online shopping, we might use PayPal or Bitcoin. This approach allows us to flexibly choose different payment methods as needed without modifying the shopping cart or product code. So, when should you consider using the strategy design pattern? If you have multiple algorithms to choose from and want the flexibility to switch between them at runtime, the strategy pattern is a great choice. By separating the algorithm selection from the client code, you can make your code more flexible and easier to maintain. This pattern is particularly useful in scenarios like payment processing, sorting, or data processing, where changes to the algorithm won't impact other parts of the system. To summarize, the strategy design pattern encapsulates algorithms in independent classes, allowing them to be used interchangeably without modifying the client code. This design pattern increases system flexibility and maintainability, enabling us to easily choose or change algorithms at runtime. Hello everyone, welcome back to the ByteVigor channel. Today, we're going to explore the state design pattern, a widely used behavioral design pattern in software development. The core idea of this pattern is to change the behavior of an object based on its state, allowing the object's behavior to evolve as its state changes. Imagine you're using an automatic coffee machine. This coffee machine handles your requests differently based on its current state. Initially, the machine is in an idle state, waiting for you to select a coffee type. Once you make a selection, it switches to a preparing state and starts making the coffee. After the coffee is ready, it moves to a completed state, waiting for you to collect your coffee. In each state, the coffee machine behaves differently. The state pattern is like this coffee machine, managing an object's different states to change its behavior accordingly. According to Wikipedia, the state pattern is a behavioral design pattern that implements a state machine in an object-oriented way. With the state pattern, each state is implemented as a derived class of a state interface, and state transitions are handled by invoking methods defined by the interface. The state pattern can be seen as a variant of the strategy pattern, where the current strategy changes based on state transitions. To better understand this pattern, let's use an automatic coffee machine as an example and implement the state pattern in Java. In this example, the coffee machine's behavior changes based on its current state, which includes idle, selecting coffee, and dispensing coffee. Note that this is a simplified example, and an actual coffee machine would have more complex states. First, we define a coffee machine state interface, which contains the various operations that the coffee machine can perform. These operations include inserting a coin, selecting coffee, and dispensing coffee. Through this interface, we define all possible actions for the coffee machine, but the specific behavior will be determined by different state classes implementing this interface. Next, we create concrete implementation classes for each state of the coffee machine. These include the idle state, selecting coffee state, and dispensing coffee state. Each state class implements the coffee machine state interface and defines the behavior of each operation according to the specific state. In the idle state, if the user inserts a coin, the system prompts, "Coin inserted, please select your coffee," and switches the coffee machine state to selecting state. If the user tries to select coffee or dispense coffee, the system prompts the user to insert a coin first. In the selecting state, if the user inserts a coin, the system prompts that the coin has already been inserted and not to insert it again. If the user selects a coffee, the system starts making the coffee and switches the state to dispensing state. If the user tries to dispense coffee, the system prompts the user to select a coffee first. In the dispensing state, if the user inserts a coin or selects coffee, the system prompts that the coffee is being made and not to repeat these actions. If the user chooses to dispense the coffee and the coffee is ready, the system prompts the user to collect the coffee and switches the state back to idle state, ready for the next operation. Next, we define the coffee machine class, which manages the different states of the coffee machine and executes the appropriate actions based on the current state. The coffee machine class maintains different state objects internally and tracks the current state through the current state variable. Each time the insert coin, select coffee, or dispense coffee methods are called, the system performs the corresponding action based on the current state and switches to the next state if needed. The state transitions are handled by the setState method. Finally, in the client code, we create a coffee machine object and sequentially execute the actions of inserting a coin, selecting coffee, and dispensing coffee. In this example, when we call the insert coin method, the coffee machine transitions from idle state to selecting state and prompts the user to select coffee. When we call the select coffee method, the coffee machine enters the dispensing state and starts making coffee. Finally, when we call the dispense coffee method, the coffee machine informs that the coffee is ready and switches back to idle state, prepared for the next use. So, when should you consider using the state design pattern? If an object's behavior depends on its state and needs to change dynamically at runtime based on state transitions, you should consider using the state pattern. This pattern is particularly useful in systems with complex state transition logic, such as automatic coffee machines, vending machines, or order status management. By using the state pattern, you can separate state and behavior logic, making your code more organized, maintainable, and extensible. To summarize, the state design pattern separates state and behavior, allowing objects to dynamically adjust their behavior based on their state. This pattern improves system flexibility and maintainability, enabling easy management and extension of an object's state logic. Hello everyone, welcome back to ByteVigor. Today, we are going to explore the template method design pattern, a very common behavioral design pattern in software development. The core idea of this pattern is to define the skeleton of an algorithm, allowing subclasses to redefine certain steps without altering the algorithm's overall structure. Imagine you are a chef who needs to prepare a meal. The process of cooking usually follows a fixed pattern, including steps like preparing ingredients, cooking, and serving. However, the specifics might vary depending on the dish you're making. For example, the preparation steps for soup and stir-fry differ, but the overall process is similar. The template method design pattern is like this cooking process, where you define a general procedure and allow customization of specific steps. In simple terms, the template method design pattern lets you define the general structure of an algorithm while deferring the implementation of certain steps to subclasses. According to Wikipedia, the template method is a behavioral design pattern that defines the skeleton of an algorithm in a base class, allowing subclasses to redefine specific steps without changing the algorithm's structure. Now, what is the difference between the template method and the strategy pattern we learned earlier? Both patterns deal with defining algorithms, but their focus is different. The template method emphasizes defining the structure of an algorithm within a common framework, allowing subclasses to override parts of the process as needed. It focuses on a fixed process rather than choosing between different algorithms. On the other hand, the strategy pattern emphasizes the interchangeability of algorithms. It allows you to choose between different algorithm implementations at runtime without affecting the structure of the algorithm. In other words, the strategy pattern encapsulates each implementation in separate classes, making them interchangeable through interfaces, while the template method achieves partial customization through inheritance. To better understand this pattern, let's take a simple example of brewing coffee and tea implemented in Java using the template method design pattern. First, we define an abstract class caffeine beverage that contains the template method prepare recipe. In this method, we outline the general steps for brewing a beverage, including boiling water, brewing, pouring into a cup, and adding condiments. The specific steps for brewing and adding condiments are left for the subclasses to implement. Next, we create two concrete subclasses, tea and coffee, which implement the abstract methods in the caffeine beverage class. The tea class implements the steps for brewing tea and adding lemon, while the coffee class implements the steps for brewing coffee and adding sugar and milk. Finally, in the client code, we create instances of tea and coffee and call the prepare recipe method to brew the beverages. In this example, the caffeine beverage class defines the general process of brewing a beverage, and the specific steps are delegated to the subclasses. The tea and coffee classes each implement their own brewing and condiment adding methods without affecting the overall process. As you can see, the template method design pattern ensures consistency in the algorithm structure while allowing flexibility in specific implementations. So, when should you consider using the template method design pattern? This pattern is useful when you have a general process that needs to be shared among multiple classes, but certain steps need to be customized based on specific requirements. It's especially suitable for scenarios where you need to define an algorithm framework but allow different implementations, such as data processing workflows or document generation processes. In summary, the template method design pattern allows you to define the skeleton of an algorithm, enabling subclasses to redefine certain steps without changing the overall structure. It enhances code reuse and flexibility, making it easier to apply the same algorithm framework across different scenarios. Thank you for watching this video. If you found it helpful, please like and subscribe to ByteVigor and make sure not to miss our future content. See you in the next video.